Hi friends, welcome back. Today I'm going to start compensator and controllers. So till now we completed up to state space analysis, and I hope that you people will be okay with the questions. Please start practicing. This is the last unit we are starting today. You have so many units to finish. Start practicing. And one point is, if you are from the electronics and communication, you can prefer the previous year gate papers of EE instrumentation. If you are from instrumentation or electrical background, you can do the same thing. Okay, it will enhance you. Don't go here and there. If you will follow, suppose for example, suppose you are studying the control system particular, and in that you are practicing the root locus. If you are from EC background, you will find some question in your previous year booklet of the gate, isn't it? Suppose you are getting 30 questions. Okay, 30 questions are over. But if you will take the question paper of instrumentation and electrical, you will having 90 questions. If I am assuming that 30 question in each, so you will be having 90 questions. And the standard of instrumentation papers, basically I'm saying, is very high. You will get good number of questions there, and the level of questions will be very high. Then second level is EE, and the third level is EC. EC people, you are getting easy questions. So when you will get to know this, whatever I am saying is, then you will prefer 3 different books. And books for what? For get previous year papers. Hardly it will be 450 or 500 rupee for each. I'm saying, if you are from EC, definitely you will be having EC get papers. But please purchase the instrumentation and electrical also. Okay, it will help you, not me. I'm saying for you only. Okay. So today we are going to start the compensator and controller. So first we'll see the purpose. What is the purpose? The purpose is, now if the system is unstable, we can manipulate this condition by using compensator and controllers. So compensator and controllers, these are some mediator kind of thing. They are going to make some bridge between 2 points, and these 2 points for me, for the control system, is nothing but input and output. You are applying something, you are getting something. And if your system is an unstable system, I can manipulate that. Your compensator and controllers are able to manipulate the system. They can make the system stable, or the stable. If you have the stable system, you can change the the parameters of the system, okay, to get the desired output, isn't it? Now it's kind of for the real time example, how I can compare this. Suppose about the table fan. The table fan is working in your room, and the speed is 5, level 5 I'm talking about, but you do not require that much. You can control that, you can reduce the speed up to 2. So according to that, your system will work. This is the fully controlled system, that's why. So compensator and controllers are basically to control the system parameters to get the desired output, isn't it? This is the definition of this. Now separately we will discuss about the compensator and controller, but before that, let's come to the purpose. And the first point is, if the system is unstable, we can manipulate this condition by using compensator and controllers. Later we'll see how. Okay. Second point is, if the system is stable, then also we can manipulate and can get the desired performance. Whether it's unstable or stable, we can change, we can manipulate. It's kind of person who always do the manipulation. Okay. So the third point is, generally type 2 and higher order system are an unstable system. Generally, if you'll see, if the type is 2 or the higher order system are unstable in general, so we can manipulate these systems by using lead compensator and can get stability and required performance. So here I'll use the lead compensator. Later we are going to discuss about the lead compensator, don't worry about this. So we can get the stability. See, second type or higher system are unstable in general. How we will manipulate that and will make the stable system, later we'll discuss about that. Okay. And the next point is, for the stable system, by changing the gain K by compensator and controller, we can get the desired performance. So we have the gain K in the stable system. So on the gain K, there are so many things which are going to depend, like zeta. like your damping ratio, that is nothing but your frequency of oscillation. These two things are going to depend on K, and if you are going to control these two things, it means you can control the entire process of the system, isn't it? You know very well, for the various values of zeta, the system will be underdamped, undamped, overdamped, and critical damped. So you can control the zeta, you can control the K, but how? By using controller and compensator. We'll discuss about that, don't worry. So let me start now. Okay, see, for example, I'm taking this. You have the open gain GS given, K divided by A square, S plus 1, S plus 2. Order is 4, type is 2, and the feedback element is given 1. When you will find out the closed loop control system, you'll get this. So this is nothing but characteristic equation in denominator, isn't it? So by looking to the characteristic equation, I can conclude over the stability, isn't it? So this system is unstable system. How I'm saying like this? You can check by RS table, or easily you can check, see, S to the power 1 term is missing or not. And we studied in the RH criteria, if anything is missing, any power of S is missing, it means system will be definitely an unstable system. You can check this system, but what I said earlier is I can make this system stable by using PD controller. What this PD controller is, later we'll discuss about this, but for the time being, just remember the thing is, the PD controller is nothing but KP plus KDS. Don't worry, just remember it. सारी चीज मक्खन की तरह क्लियर होगी, don't worry. Okay, so here is the PD. Now this PD I'll include into the system in the series, so this will be multiplied with K. Okay, so your closed loop control system will be, when you will add this into the system, it's like this. Initially you have GS into the system, and this is unity feedback as it's given in the question itself. Okay, now this PD I'll add here or here. Here I'll add PD, and that is you have to add KD plus KDS. This is KP actually. Okay, so you are adding this. Now when you will find out the control system or the closed loop control system after adding PD, what you will get, you can do this for me, so please do it. So you will find that here this is KP plus KDS in numerator. In denominator you will get S to the power 4 3s square plus 2s square plus KDS K plus KP. You will get like this. Okay, now this system becomes a stable system. The system is same, everything is same. Here is the system. You are just adding one PD controller and you are making the system stable system. So what is this? This is the application of compensator controller. You can manipulate the system, isn't it? So let's come to the compensator. So what is the compensator? A compensator is an electrical network. This is not right. An electrical network which adds final pole and finite zero to, oh my god, what is this? This is finite poles and finite zeros. Okay, finite pole and finite zero into the system, isn't it? So compensator, how to compensate the system, how to manipulate the system. If you have the unstable system, in the previous example whatever we have seen, what we have done is we just added one PD controller or the PD element, isn't it? So we are negotiating with the stability, isn't it? Initially the system is unstable, you are making it stable. So the point is we are going to add some poles or zeros into the system, right? So we have some types of compensator. One is lag compensator, lead compensator, leg lead compensator and lead leg compensator. Okay, so one by one we'll study all these four compensators. So what is the definition of compensator? The definition of compensator is we can manipulate the system performance by adding some finite pools or zeros, isn't it? So now the first point is the lead compensator I'm talking about. If sinusoidal input applied to a network and it produces sinusoidal steady state output having phase lead with respect to input, then this network is called the lead network. What it means, see, here is the system, this is your system. Okay, to this system you are applying some input. Suppose let's take you are going to apply phi t plus theta and the output, and suppose this is the sinusoidal sine omega t. Let's take like this, or you are not confused, I'll take like sine omega t plus theta. I'm taking like this. At the output also you'll get the sinusoidal output, but with phase lead. Means here I'll get, suppose I'm getting theta plus pi by 2. Here pi by 2 leading is there. So input is lagging by pi by 2 and output is leading. So according to the lead compensator definition, if you are going to apply the sinusoidal input to the network and produces sinusoidal steady state output having phase lead with respect to input, then this network is called the lead network. Okay, actually lead network is nothing but the high pass filter or working as a high pass filter. Wait a minute. The lead network speed up the transient response and increase the margin of system stability. Okay, so actually you have to remember this. Lead compensator works is high pass filter. High pass filter. Okay, how many letters here? 1 2 3 4. How many letters here? 1 2 3 4. So lead compensator is nothing but the high pass filter. So the characteristic of this, don't worry, later we'll see in details. In the lead, I'm telling you the output, how we'll get the output. It will be like high pass filter, like this you'll get, isn't it? You'll get like this. So the diagram, if I'll see, or the circuit or the network for the lead compensator, the circuit is given by this. So here is the network given. See, now what you have to do is you have to find out V0 by Vi, the transfer function, isn't it? So V0 is divided by VIS. How you will find out? R2 into VIS divided by R2 plus parallel combination of R1 and 1 by SC1, isn't it? So when you will solve this, what you will get is, directly I'm writing, please you can do this. I think you all are smart, okay, so you can do. So what you will get is R2 1 plus SC1 R1 divided by R1 plus R2. Now in bracket 1 plus R2 R1. Don't worry, this is not important, okay, don't worry. So this is kind of transfer function for the given network you will get, okay, when you will solve with that network. So here if I'll convert this into the standard format, this one is very important. 6 to 8 times you have questions from this background. V0 Vi, the standard, or the, I can say, the transfer function of the lead compensator is given by alpha. This thing is nothing but just equating by alpha. So this is alpha inside 1 plus S tau, means this R1 C1 I'm taking tau. So my replacement is R1 C1 and the alpha is nothing but R2 R1 plus R2. Okay, so the standard format is this. here 1 plus alpha is given, so alpha, and tau is also coming here, so tau and s. This is the standard transfer function for the lead compensator. Okay friends, this is the lead compensator formula or the format. You have to remember this always. So actually for this alpha coming into the system is nothing but the attenuation. Okay, if anything is going to multiply with the magnitude of system, it means we have the attenuation. Okay, what I'm saying is, suppose at the input stage you are applying 10, at the output you are getting suppose 8, so it's kind of your system is, you know, your input is attenuated. Okay, so here also your output is going to multiply with the alpha, some constant quantity. So this is attenuation into the system. For the lead compensator, the optimum value of this alpha is 0.1. Okay, so 0.1 is the value. So friends, actually first the output of the lead compensator is what? This is the attenuation, and I have to remove this attenuation. So what you will do, the output of the lead compensator, this is the lead compensator, we are getting output from this, and you will apply this output to an amplifier stage whose gain is 1 by alpha. Now you will get your output which is unattenuated. This alpha will be removed now. Now what you will get is, V0 is nothing but, you are getting here, this is the actual thing you have to remember now. Forget about that attenuation constant. 1 plus s tau divided by 1 plus alpha s tau, isn't it? Now your function is V0 is VIS equal to 1 plus, please remember this, 6 to 8 times, 1 plus 6 to 8 times. I'm saying you got the questions in GATE exam. Okay, so 1 plus tau s divided by 1 plus alpha tau s. For the lead compensator, this alpha is always 0.1 and something. Okay, so when you will do, or you will keep here, so the poles and zeros location will be like, wait a minute, you will get this, isn't it? Your 0 will come here, your pole will come here. Why? Because alpha is less than 1, that is 0.1 here. So 0.1, it will become minus 10 by tau. So minus 10 by tau obviously will come to the here only, isn't it? So for the lead compensator, 0 is near to imaginary axis, or the 0 is near to origin, you can say. Okay, so please note down this point. This is very important one. 0 added near to origin, see here, and pole added away from the origin. Okay, so this is the point for lead compensator. So for the lead compensator, it's kind of high pass filter. In the high pass filter, the third point is 0 added near to origin and pole added away from the origin. You can see here, this is 0 and this is pole, and this is very important thing, that is the transfer function of the lead compensator, that is 1 plus tau s divided by 1 plus alpha tau s. This is the standard format you have to remember. So we have only one disadvantage of the lead compensator, and that is, you know, it creates the attenuation into the system, and we know very well, to remove the attenuation from the system, we are going to apply the series amplifier whose gain is 1 by alpha, or 1 by attenuation constant. Okay, so for the lead compensator, optimum value of alpha is 0.1. This alpha value is 0.1. This is the optimum value. Okay friends, now if you have transfer function like this, can you draw the Bode plot? Yeah, definitely you can. So here is the Bode plot I'm drawing for the lead compensator. Okay, so this will be the, you can take this plot here also, some DC will be added or magnitude will come, but to show the high pass filter I don't like this. Okay, there will be no change in the system output. See, at 1 by tau the standard function was s tau 1 plus alpha s tau, isn't it? Now at tau means 1 by tau, you are getting the standard format is 1 s t1, isn't it? And you can write like this also, omega 1. So I showed you this format, you have to write in this way. So directly the denominator term, this term you can say this is the frequency. So frequency for this question will be 1 by tau. So at 1 by tau you are getting 10, that is 20 dB per decade, you will get the slope, isn't it? When you will add the 0, 10, 20 dB, 20, 40 dB, 30, 60 dB. 1 pole minus 20, 2 poles minus 40, 3 poles minus 60, like this, isn't it? So this is kind of HPF or not. The characteristic of this lead compensator is just similar to the HPF. Okay, now here one thing is very important. In between these two frequencies you have the omega max or optimum value, and that is given by under root of this 2, 1 by tau, 1 by alpha tau. Geometric mean of this 2, I'm sorry, not geometric mean, see, the multiplication of this 2 and you will take the under root of these two quantities, you will get the omega max. This is very important. 3 times you got the questions from this. Okay, so to know any transfer function which filter, then draw the Bode plot. If you are looking to find out the transfer function or the characteristic, whether it's LPF, HPF, all pass or whatever, so you need to draw the Bode plot, so you'll get the idea. Okay, similarly for this system, if you draw the phase plot, the phase plot will be like this. At this frequency you'll get plus 90, isn't it? Why? Because you are adding 1 0 and here it will be minus 90. Okay, so you have maximum phase also. So this omega max is nothing but this, or in the format I can write like this, omega max is nothing but under root of omega c1 into omega c2. In two corner frequencies, in between two corner frequencies you will get the optimum value of omega max. Omega, I can say this omega max. Okay, and what about the phi max? Phi max you will get sine inverse 1 minus alpha divided by 1 plus alpha. Okay, I need this quantity with positive sign, so definitely I'll take 1 minus alpha, not alpha minus 1, because you know very well the alpha is less than 1. Okay, so 1 minus alpha and this, so this will be phi max. Actually this will be phi maximum. Okay, so friends, for the lead compensator you have to remember how many things? For the lead, wait a minute, for lead compensator you need to remember this is working as a high pass filter. The transfer function for the lead compensator is given by 1 plus s tau divided by 1 plus alpha s tau. Okay, where alpha optimum value is given by 0.1. Okay, and omega max is given by these two frequencies. Very easy, omega c1 into omega c2. In this case it's 1 by alpha tau into 1 by tau, isn't it? So 1 by tau you can take out, it will be 1 by alpha, and you will get phi max also. So phi max will be sine inverse 1 minus alpha divided by 1 plus alpha. So this is all about this class. In the next class we'll meet and we'll discuss the effects of lead compensator into the system. Okay friends, we'll meet in the next lecture. Till then, take care and bye.